Hello everyone. Today we are going to see about registers under Digital Principles and Computer Architecture. First of all, what is meant by a register? A register is a temporary storage that is placed inside the processor itself. If there is no register, the arithmetic and logic unit has to go and access data from the memory, and then it has to process, and then it has to store the data back to the memory. This makes delay as well as it makes complexity for the arithmetic and logic unit. The placement of registers inside the processor makes the ALU can access the register easily and locally. So the data transfer becomes faster and the operation becomes efficient. A register is a group of flip-flops with each flip-flop capable of storing one bit of information. And so that if the register is of 8 bits, then it contains 8 number of flip-flops and it can hold 8 bit of binary information. And in a register, it can contain flip-flops as well as combinational gates that perform certain data processing tasks. If the register consists of a group of flip-flops and gates that affect their transition. The flip-flops hold binary information and the gates control when and how new information to be transferred into and from the register. There are various types of registers available commercially. The simplest one contains only flip-flops with no external gates. This is a typical logic diagram of a register with 4 flip-flops. So the size of the register is 4 bits. The flip-flops are of D flip-flops here. It contains a common input clock pulse along with individual input lines called as I0 through I3, and there is a clear input which is connected to a special terminal of each and every flip-flop, and each flip-flop has its own output lines called as A0 through A3. The common clock input triggers all flip-flops on the rising edge of each pulse. The binary data that is available at 4 inputs are transferred, 4 inputs that is from I0 through I3 are transferred into the flip-flops, D flip-flops or the 4-bit register. The 4 outputs can be sampled at any time in order to obtain the binary information of the 4-bit register. And there is a clear input which goes to 0, that makes all the flip-flops reset asynchronously. Thus the clear input is useful in clearing the register, the content of the register, when there is the data inside the register is of no use, and the clear input must be maintained at the logic level of 1 during normal clocked operations. The clock signal enables D inputs from I0 through I3, but the clear input is independent of the clock signal. The transfer of new information into a register is referred to as loading the register. So if all the bits of the register from I0 through I3 are loaded simultaneously, we say that the loading is done in parallel. A clock transition applied to the C inputs of the register will load all 4 inputs from I0 through I3 in parallel. In this configuration, the clock must be inhibited, that is stopped from the circuit if we want the content of the register to be left unchanged for a while. Register with parallel load. Most registers or most digital systems have a master clock generator that supplies a continuous stream of clock pulses to the system. The clock pulses are applied to all the flip-flops in the register, and they act like a pump that supplies a constant beat to all the parts of the system. A separate control signal must be used to decide which specific clock pulse will trigger the particular register. So this is a logic diagram of a parallel load register. So here we are having a common load input with its inverter, and then the previous input lines I0 through I3, and then there is a clock pulse along with a buffer which is connected as a common line to the 4 flip-flops. And again we are having the 4 output lines from A0 through A3. The C input receives the clock pulses at all the times. The buffer gate in the clock input reduces the power from the clock generator. That is, the buffer can hold the data for a certain number of time, so that the clock generator can reduce the power. And the load input finds the action to be taken with each clock pulse. When the load is set as 1, the inputs are transferred to the register. When the load is set as 1, the inputs from I0 through I3 are transferred to the register with a positive clock pulse. Again, when the load is set as 0, the inverted line of the load is connected with the D flip-flops, so that here the D flip-flops are connected with their output. That is, the feedback connection of D flip-flops are connected with their input, so it maintains no change condition. With each clock pulse, the D input determines the next state of the input. To leave the output unchanged, it is necessary to make the D input equal to the present value of the output. The load input determines whether the next pulse will accept new information or leave the information in the register intact. The transfer of information from the inputs into the register is done simultaneously with all 4 bits during a... Now we are going to see shift registers. A register that is capable of shifting its binary information in one or more directions is called as a shift register. If the register is shifting the bits in one direction only, then it is called as unidirectional shift register. If the register is shifting its bits in both the directions, then it is called as bidirectional shift registers. And a logical configuration of a shift register contains a chain of flip-flops connected in cascaded form. That is, the output of the first flip-flop is connected as input to the second one, and it continues, it goes on up to the number of flip-flops or the size of the register. All flip-flops receive common clock pulse that initiate the shift from one stage to the next one. The simplest possible shift register is one that uses only flip-flops. The output of the given flip-flop is connected to the input of D input of the next flip-flop, and so on. The ultimate output is taken out from the leftmost flip-flop if it is of right shift register, and vice versa. Now we are going to see a bidirectional shift register with parallel load. A register that is capable of shifting its bits in both the directions, then it is called as a bidirectional shift register. The most general shift register includes an input clock pulse to synchronize all the operations, a shift operation, shift right operation, a shift left operation, a parallel load operation, n parallel output lines, and a control state to retain the register content. Here it is a simple 4-bit shift register. It has a single serial input which is connected as input to the first D flip-flop. The output of the first D flip-flop is taken as input to the next one, and it goes on. And finally we are getting the last output from the output line of the last flip-flop, and the common clock pulse is connected with all the flip-flops, which enables the flip-flops. And here is the bidirectional shift register with parallel load. Here we are having 4 number of D flip-flops, and each flip-flop has its own corresponding multiplexer of 4x1 in size. That means it has 4 inputs and 1 output. The 4 inputs are, when the input number is 0, it means the input is taken as feedback from the output of the D flip-flop. And then if the input line is 1, means it is the serial input for the first one. And the second one, for the second one, the input line is 1 means it is the feedback from the previous D flip-flop, that is shifting to the left, shifting downwards, that is left shift right. Here this is the function table for the given bidirectional shift register. So the selection lines S0 and S1 selects any of the inputs among 0, 1, 2, that is input line 1. For the first flip-flop, we are having input line 1 as the serial input. For the second one, the input line is taken as the feedback from A0, that is shifting in downwards. For the third multiplexer, the input line 1 is the feedback from A1 and so on. So the combination 0 and 1 means shifting right, that is downwards. Similarly, the combination of selection inputs 1 and 0 means shift left, that is in upwards, that is it will select the input line 2, which is for except the fourth multiplexer. The other multiplexers, for the other multiplexers, the input line 2 is the feedback obtained from the next multiplexer, so it is shifting upwards. When the selection lines becomes 1 and 1, then all the I0 through I1 lines are selected, then the parallel load is being performed. Thank you.